of really standard functional programming reasoning after we have called these tactics that that decompose everything we know about the hypotheses that mention the operational semantics of Kami. So in short, yep, that's really an invariant, and we can prove this even shorter version of the property that says for any reachable state the invariant holds, and that mostly appeals to that inductive lemma we just proved. All right, any questions at this point? All right, so that's, let's say, the first half of proving that we can combine the first two stages. What I want to do next is we're essentially going to do a simulation proof like the ones that we saw yesterday for the software-style message passing language. Key thing we'll need to do is provide the equivalent of the simulation relation. In this setting, that will turn out to be a mapping from register values in the fancier optimized system into register values in the simpler spec-like system. And we'll want to show that as we run the fancy system, we can keep matching all its steps in the spec where this mapping continues to hold at every step of this joint execution. So what I'll say here is, so IR is the registers in the implementation, SR is the registers in the spec. And I'm going to give a relation that connects them. And this example is showing doing that with tactics, which kind of help with some of the dependent typing complications. I want to assert that this mapping is going to assume that the data register in the implementation contains a value called data v that has type bit data size. And also, the ELT register of FIFO1 contains a value called ELT-v, which is a list of bit vectors. Therefore, knowing that, I'm going to assert that the spec level registers can be reconstructed from these two values. The spec only has a register called data, and what does it contain? It either contains the first element in the queue, or if the queue is empty, it contains the current value of the data register. That's kind of the most non-obvious part of this proof, though it isn't terribly complex. So this is the simulation relation part of our argument. One last thing we need to do, we need to explain for each rule in the implementation which rule in the spec corresponds to it, and that's pretty straightforward in this case. We just have these slightly different names, but both kind of give it away by saying the word double inside of them. And now we should be able to prove this simulation. So first, I want to say, let me substitute the left-hand side of this relation with the inline version, which I generated before. I'll give the name of the inline version I made, so now we have the inline version. And then I effectively apply the general simulation principle. This k-decompose R no defs is like a special kind of induction for this setting, where I have to give it the register map that relates the implementation and spec worlds, and the rule map that tells you how the different kinds of steps correspond to each other. And then I'm in this state where I have to consider an arbitrary reachable state called OIMP and consider one step that OIMP can take where it runs a rule. And I'm then going to show that the spec can match that behavior such that the register map we defined remains satisfied afterward, given that we know up here that it was satisfied beforehand. So I'm not going to go through all the details of these proofs, but it won't be too strenuous. So first thing I want to do is use the invariant we proved. I proved the invariant with this lemma, so I'll just use that with our k-inv add tactic, and the invariant is going to pop into existence here. We know this invariant because we're in a reachable state. Invariants, by definition, hold of all reachable states. That's the only invariant I need, so I'll call k-inv add end, and the reachability fact here will disappear. And then I'm going to call k-invert to analyze the code of the module we're verifying and compute from this substep what are all the legal effects that might happen from running one step. And we'll get two cases because there were two rules in the program. For instance, in this case, we now have the code for the produce rule inlined in a hypothesis, which is known to equal the action A that is actually being run in this hypothesis. So I can zoom in on this case. I call the somewhat opaquely named KINV magic with tactic, which is where we're using our custom forward reasoning tactic, which gets plugged into a more general procedure. And this is going to invert the fact that we ran this code with this relation, and it'll just figure out the effects of running it. In particular, well, let's see, we got a state called CSIMP, which is mentioned in the last argument to substep down here. So now if we look at the last argument to substep, well, it even figured out what to do down below there. It only requires us to prove this simple implication in functional programming that two different expressions using head are actually giving the same answer. And it turns out this one follows pretty directly by case analysis on a variable x0. And then something similar happens in this other case. We don't have to do any manual reasoning about the semantics of Kami because there are these inversion tactics and that will do all that stuff for us. All right, so I proved that the two-stage system can be merged into one stage. And what can I do with that? We can make a little more progress on our original goal. The proof we looked at before, let's see, impl inspect 2, is that what we just proved? No. We can get up to a point by descending modularly through the structure of the designs to using the impl 120k theorem that we proved, which will show we can merge stage 1 and stage 2 together. That's good. And that leaves us with this point where we're trying to, ooh, that's not good, trying to show now we have a system where the first two stages are merged together. There's just one queue left, and there's also the third stage. I want to show that this system refines the original spec. So we'll need to do a little more work to set up to finish this proof with some lemmas, but any questions here? All right, let's abort this one for now. You might have guessed if I've started with merging the first two stages, we should now probably merge in the third stage. So let's think about that. Let's consider a system that has the first two stages merged, a simple FIFO between them, and then third stage. And I want to just prove a theorem about this one. I'll again use a tactic to inline together the modules of it. And now I'll use the general pipeline invariant machinery, where the function that advances state just adds 1, and the function that formats to send to the world now also does the multiplication by 2. And useful lemma about that, which I won't talk about. Now the invariant is pretty similar to before. It is, we have contents of the data register and the list that is inside the FIFO, and therefore we have if we take the contents of the FIFO and then add 2 times data value to the end, this satisfies the pipeline invariant. So this will always be true as the system runs. And then I define very similar looking tactics customized to this invariant for the forward and backward directions of reasoning, and use them to prove another invariant property here with very close to the same proof script, except for some of the fine details of this list reasoning in the middle. So let's fast forward past that. And this one, so we've proved that invariant holds. Now we need to give the simulation relation that tells you how to essentially get the state of the spec from the state of the implementation. So this time we say the data register has contents, the ACK register has contents, the queue has contents. Well then, there should exist some other data value that, well, skipping to the bottom or not, let's see. So the state of the spec says the accumulator contains exactly the same accumulator as in the implementation. But the data register contains something else, S data V, something that we quantified existentially here. The thing we know about S data V is when you double it, that's the same as either the first element of the FIFO or twice the original data value, if the FIFO happened to be empty. So again, this is something that's maybe not entirely trivial to come up with, but once it's written out here, then it doesn't take many characters to write it, and the proof won't be too bad. And again, we have to give this mapping of rules in the implementation to rules in the spec. So then I can prove this simulation with essentially the same kind of sequence of tactics I used for merging the first two stages. So I won't dwell on those again, and then there's a bunch of list reasoning in here my word for it. All the detailed, proof-specific lines of tactic script here are about list properties, functional programming stuff, not about the details of the Kami language, syntax, or semantics. So now with that one, we are ready to finish off this proof. And some transitivity, some more transitivity. Descend under a plus plus, use our first stage merging fact, reflexivity, more transitivity, blah, blah. Use the fact that fancy FIFOs implement their spec. And finally, we get down to the point we've descended enough, we can use the second two-stage merging lemma that we proved separately. So that's our main theorem. So notice what we did. At some level, we took the spec, we showed a way to decompose it into parts so that we could tackle those parts separately. We used transitivity. We used substitution of the spec of a library module for the implementation of that library module. And at certain points, we used some manual simulation arguments about successive stages in a sequence of versions that we broke the system into to justify the larger transformation from the implementation to the spec. Any questions here? Yeah.
If we were to change the order in which we sort of abstracted the FIFOs, how would that change the proof?
Abstracted. Oh, I see.
So we did the
right.
last one first, I think, and then the right one.
Okay, so that sound. Well, okay. The order I was doing them in is I decided to merge the first two stages first, so I substituted their FIFO first, so that I can do this proof about impl 1, 2, where I can perform this inlining and get the spec level version of the FIFO inlined rather than the more complex implementation ready version of the FIFO, which I would then have to, if we look at the invariant that I stated here, it is, I only had to talk about the one register of the FIFO here because I inlined the spec of the FIFO before proceeding to this stage. If I had not done inlining, I would have had to write a much more complicated invariant that talked about the 4 different registers of the FIFO and the kind of the pointers that go around and around in an array. And that would really have been a distraction from what's actually happening in the 2 pipeline stages and what makes those correct. Other questions here? Yeah?
How does it happen that the final depth of the physical FIFO goes away?
Ah, right. I didn't have to think about properties like what happens when the FIFO runs out of space. And the answer to that is that the BlueSpec compiler underneath this takes care of that for us. It just never runs rules when preconditions of methods that are being called would be violated, and it generates this scheduler circuit that we talked about yesterday that embodies that logic. But from our perspective here, we can just rely on the operational semantics of Kami, which builds in the fact that steps that involve violating preconditions are not allowed, so we only have to think about valid steps. And then maybe it's useful to quickly bring up the actual implementation of FIFOs. Recall we had these little assertions like assert not is full for the enqueue method, assert not is empty for the dequeue method. So this is how we're telling the BlueSpec compiler when it's okay to allow one of these actions to run. And it takes care for us of scheduling that respects these constraints. Other questions here? Yeah?
So the behavior of the scheduler is something verified by BlueSpec, is that correct?
There are no verified schedulers at the moment, but in the final grand realization of these plans, there will be a verified compiler that implements scheduling.
Okay.
Yes?
Oh, sorry, I think it's still a bit more complicated. As far as I remember, initially we had a thing which just increments counter, and so that the counter implementation is then also basically blocked when the queue is full. That's what you're saying. In the BlueSpec implementation takes care that if the queue is full, the counter is not incremented.
Yeah, right. So in this first stage, we have some code that wants to increment, and it needs to call the enqueue method in the course of doing that. If the queue is full, then this rule will not be allowed to run. Likewise for the other stages. And also, stage 2. this rule will not be able to run if the queue is this queue is empty. So this rule requires this queue is empty and this queue is not full. We don't have to think about that just because of by virtue of the way the code is written. The compiler understands that's the behavior that should happen. Other questions? Yes.
I'm looking at the proof of the sync FIFO refines not sync FIFO, and it's really long.
Sorry.
I know, not sorry. I guess that's. Could you just comment briefly on what sort of things you have to do in order to do something like just carry that proof out? Because that seems to be the hidden crux of proofs that you showed here.
So the question is, what is complicated about the proof that the optimized FIFO implements the imaginary functional programming FIFO? I think that would be an interesting proof even about pure functional data structures on both sides in Coq. And we don't need to do it too often. So, yeah. I think it's reasonable that that's not a trivial proof. I haven't actually looked at the details lately of that. Let's pull it up and see how scared we are. How many pages? It looks like a lot of what's going on here is reasoning about arithmetic with bit vectors and maybe showing we don't overflow in bad places and things like that. Not too bad, a few hundred lines. We could probably automate more of this, but it's not clear it's worthwhile because this proof is probably not representative of the average module proof. But at the same time, if you have to write 500 lines for every new data structure, I think that's fine. The data structures don't tend to come along too often.
So do you reuse data structures?
We reuse this FIFO everywhere, yeah. Other questions?
I guess, is this require like manual proofs every time you're just like, joining the FIFO to something? Is there a way to, I guess, automate that construction?
Are you suggesting we should have a tactic that embodies an automated proof strategy for pipeline stage merging or something like that?
Yeah, possibly. Like, is that
It's conceivable.
something that would make sense?
If it is possible to build, it would be great to have it. I'm not sure at the moment how hard it would be to build that tactic. Yeah.
And one more question. Assume you have a requirement that the counter has to be incremented every clock cycle and it has to be distributed, and you basically just have to prove that your FIFOs and whatever you have in between is able to handle that. How would that look?
All right, so I think you're talking about, this might be an example of a liveness property, or not, as came up in the last lecture. We want to make sure that we don't, so the scheduler currently gets wide latitude and is allowed to skip rules whenever it wants to. It just needs to guarantee that when it does run rules, their conditions are satisfied. We have not looked into proving the kind of property that you described, which gets into promises of running rules often enough. It seems like it should be doable, but I don't know the details. Okay. So now we have verified this code. We should at least celebrate by running it. Let me put a version of this in a definition where I've instantiated the, I think I've probably, we must have substituted concrete size parameters. This was an interesting example partly because it works for any bit width of the data flowing through your queues. Let's just pick 32. That's the 32 here. I'll assign this, I'll build the module, and then I'll call these functions which are converting it into the syntax of the actual BlueSpec language that we'll use to compile this. And then let's extract that syntax to a file called target.ml. And then I'll just change directories to where that generated code popped into. What is this target.ml that we produced? Well, it's a bunch of functions that, when run, produce a syntax tree of a particular BlueSpec program that matches what we have here. And we can see some code mirroring what we were writing in Coq. It's just been translated to OCaml syntax. So let's build that file and then run it. It's called